reduction reaction, electron transfer occurs between a reducing agent and an oxidizing agent. In these reactions, one reactant is oxidized and one is reduced. The extent of oxidation and reduction must balance. The oxidizing agent is reduced and the reducing agent is oxidized. In this equation, copper is oxidized and is the reducing agent. The silver ion is reduced and is the oxidizing agent. All equations for oxidation-reduction reactions must be balanced for both mass and charge. So, the number of both atoms and electric charge for the reactants must be the same for the number of atoms and electric charge for the products. Once the charges are balanced, you know that the number of electrons produced in oxidation is equal to the number of electrons consumed in reduction.
Now here's where half reactions come in. The equation of the whole reaction is the sum of these two balanced half reactions. As you can see, the first half reaction written above describes the reduction part of the reaction, while the other half reaction describes the oxidation part of the reaction. This leads to the net ionic equation.
This is a table of standard reduction potentials. The half reactions seen are written in oxidized form plus electrons yields reduced form. On the left side of the reaction arrow is an oxidizing agent, and on the right side is a reducing agent. The more positive the value of E, the better the oxidizing agent. This means fluorine gas is the best oxidizing agent in the table, while the lithium ion is the worst. The opposite goes with negative values of E. The lower E is, the stronger the reducing agent. So lithium is the strongest reducing agent, and fluoride ion is the weakest reducing agent.
In this reaction, we're going to be using Cu and Mg. This is just like the lemon battery lab we did during spirit. Notice the voltage is positive. We use Cu and Mg, remember. But Mg has to be combined with something that is reduced by 2. And this should give us a negative voltage. But our voltage wasn't negative, remember? And here's why. So we had Cu and Mg as our metals. Mg was oxidized, and we got a positive number. But Cu can't be reduced by 2 because of its placement on the periodic table. So something had to be reduced. It must have been something inside the lemon. Now, why a lemon in specific? What's so special about a lemon? Well, lemons are acidic, and they have H+ ions. And so the H+ ions are what are being reduced by 2. This reaction gives us H2, which is the bubbles that we see appearing on the orange. This is also a similar case. We're going to be using tin and copper this time. Notice the positive voltage. In this reaction, Sn plus 2, or we should have 2, it should be with something that's reduced by 2, and this should give us a negative voltage. But we didn't have a negative voltage. This is the same as the case with the Cu and Mg. The tin is being reduced, or the tin is being oxidized, so it's gaining 2 electrons. And the copper, which should be reduced by 2, can't be because of its placement on the periodic table. So again, the lemon comes into play. The acidity of the lemon gives us the H+ ions, which are being reduced in this case. This provides the H2 for the reaction. Also, this is another reaction where we tended to see bubbles.
A voltaic cell uses chemical reactions to produce an electric current. This electric current is produced from product-favored redox reactions, and the electrons produced by the reducing agent are transferred through an electric circuit to the oxidizing agent. Voltaic cells convert chemical energy to electric energy. The opposite happens during electrolysis, where electric energy is used to produce a chemical change. For example, the electrolysis of water splits H2O into hydrogen and oxygen.
What makes the good electrode? An electrode is a device that conducts electrons into and out of solutions in electrochemical cells. To conduct electricity, a charge must be passed so ions and metals can make good electrodes. A standard hydrogen electrode is a redox electrode which has a charge of 0 volts and is used for any cell potential calculation. Anode, a positively charged electrode that attracts electrons or anions. An anode may also be an electron acceptor. Cathode, a negatively charged electrode which attracts cations. A cathode is the source of electrons or an electron donor. It may also accept positive charged.
How do batteries die? If the current is drawn from a battery rapidly, the gaseous products cannot be consumed rapidly enough, so the cell is resistant to rises and the voltage drops. The battery dies once the voltage is all used up. Recharging requires applying an electric current from an external source to restore the cell to its original state. This slide depicts what is happening inside the battery chargers we can buy at a store for our batteries.
Electrons produced at the anode of an electrochemical cell move toward the cathode. The force needed to move the electrons comes from a difference in the potential energy of electrons at the two electrodes. This difference in potential energy is the electromotive force, or EMF. This literally means force causing electrons to move, and this force has units of volts. 1 joule equals 1 volt times 1 coulomb, and the coulomb is the standard unit of electrical charge. And 1 coulomb equals 1 ampere times 1 second.
When measuring standard potentials, there are a number of factors that can change the cell potential. For example, half cells used, the concentration of reactants and products in solution, the pressure of gaseous reactants, and the temperature. But in order to make this more simple, only consider cell potentials measured under standard conditions. These are, reactants and products are present in their standard states, solutes in aqueous solutions have a concentration of 1.0 molar, and gaseous reactants or products have a pressure of 1.0 bar.
If E cell is a measure of the standard potential for the cell, the E cathode and E anode can be taken as measures of electrode potential. Because E cell reflects the difference in electrode potentials, E cell must be the difference between E cathode and E anode, and that's where we get the red equation. Here, E cathode and E anode are the standard reduction potentials for the half-cell reactions that occur at the cathode and anode.
This is a potential ladder for reduction half reactions. Where a half reaction lays on this ladder reflects the relative ability of the atoms or ions at the left to act as an oxidizing agent. The higher the compound or ion is on the list, the better it is as an oxidizing agent. The opposite goes for atoms or ions on the right as reducing agents. The lower they are on the list, the better they are as a reducing agent. The potential for each half reaction is given with its standard reduction potential.
So this equation is very important for three reasons. 1. If you have values for E cathode and E anode, you can calculate the standard potential for a voltaic cell. 2. When the calculated value of E cell is positive, the reaction is predicted to be product favored at equilibrium and vice versa. 3. If you measure E cell and know either E cathode or E anode, you can calculate the other value. This value will tell you how one half-cell reaction compares with others in terms of relative oxidizing or reducing ability.
What kind of voltaic cells do we see in our lives every day? Batteries. Primary batteries cannot be returned to their original state by recharging, so when the reactants are consumed, the battery is dead. Dry cells have no visible liquid phase. Alkaline generate current up to 50% longer than a dry cell. Material inside the cell is basic, alkaline. Secondary batteries, the reaction in these batteries can be reversed, so batteries like this can be recharged. Lead storage battery is an automobile battery. Nickel-cadmium batteries used in cordless appliances. Nickel metal hydrates are used in electric or hybrid cars. Lithium batteries made in any shape and so fit into products such as Amazon Kindles and Apple portable devices. A great example of voltaic cells we use in our lives every day is the car battery. Have you ever wondered how the battery works? Well, we have found the answer. The car battery helps power the windshield wipers, engine starter, radio, and much more in a car. A car battery works by using reverse chemical reactions. The positive and negative terminals on the battery send a flow of electrons that helps run the car. A car battery has 6 cells. These cells are soaking in solutions of 35% sulfuric acid and 65% water. Each cell has 2 sets of electrodes and is made of about 8 overlapping plates for a total of 16 plates per cell. These plates form a compact grid. The bigger the surface of the grid, the more power. The positive grid is covered in lead oxide and the negative is covered in lead. The solution of 65% water and 35% sulfuric acid acts as an electrolyte and it transports electrons as well as reacting with the plates to form a flow of electrons that creates electricity. Each cell gives off about 2 volts, and when combined together, the whole battery gives off about 12 volts. The battery then recharges by reversing the reaction, so it's ready to use the next time you turn on the car. This works because after a few minutes, the fuel part of the car starts taking over these power shifts. This is a visual of the car battery to help you understand what exactly was going on in the last slide. You can see the positive and negative terminals, as well as the cells and each of the aspects talked about, such as the plates and the juice it's soaking in and the dividers and such inside the battery.